Welcome back to Theta. In the previous few lessons, we have learned the difference between equations and inequality and was able to solve for the solutions of some equations. In today's lesson, we will focus on indices and surds by studying the mathematical laws that govern these equations. We will also learn to rationalize Surdic denominators and solve equations involving surds. So, let's begin. An index number is a number which is raised to a power. This means that for a to the power of b, the number a is multiplied to itself b number of times. Let's illustrate this with a martial artist whose energy comes from the number of times he drinks an energy drink. Let's first begin with the drink A. The first rule in indices is a to the power of m times a to the power of n equals to a to the power of m plus n. Imagine that you want to drink m number of drinks. This will give you a to the power of m, as shown. Then assuming that you want to drink another n number of drinks, you will just have to add on to the m number of drinks that you have consumed earlier on. This can be extended to the quotient form, where a to the power of m divided by a to the power of n equals to a to the power of m minus n. You can imagine this as a person who had consumed m number of energy drinks and wants to lose some of it, so he is exercising to lose it away. Each time he moves, he will lose 1 unit of the energy drink. The second rule of indices states that a to the power of m to the power of n equals to a to the power of m times n. This can be imagined as taking m number of drinks and pouring them into a bigger cup, like upsizing them. So, your upsized drink is now called a to the power of m. Like before, the martial artist drinks n number of these. This is equivalent of him drinking the drink A mn number of times, as shown, thus satisfying the right hand side. For the next rule, it states that a to the power of m times b to the power of m equals to ab whole thing to the power of m. This can be imagined as drinking two different drinks, drink A and drink B, as shown. Like before, imagine mixing these two drinks together, a bit like the 7-Eleven Slurpee. You get a new drink called drink AB. Since you have n number of each drink, this will give us n number of AB too. As such, this indices law holds true. There are a few more laws which I will not illustrate further, one of which is a to the power of 0 equals to 1. I like to see this as if you have yet to consume any energy drink, and so your energy is only at level 1. The next rule is the rule for negative indexes. This is the reciprocal rule. Like how the negative number are reflective of the positive number on the number line, I like to see as though the fraction is a mirror that swaps the value of the denominator and numerator around. The last rule is a Surdic rule. This means that if the power is a fraction, then it can be rewritten with a rotation. We will look at surds in greater details later on. Let's take a look at an example. The first thing that you can do is to split up the power sign by removing all the plus and minus notation in the power. Then, we can try to simplify the numerator and this will give us 5 to the power of n. On the other hand, since the denominator has a minus notation, I will try to factorize out the common factor. In this case, it is 5 to the power of n. As such, this will allow us to be able to simplify our fraction. By computation, we will therefore get 5 over 4 as our solution. Now, surds are just irrational roots. The word irrational just means that the number cannot be expressed as a ratio, or more specifically as a fraction. When trying to solve for Surdic equations, you can try to solve them using identities. Previously, we made use of identities to separate out the x component of the expression from the y component. Likewise, we can do the same by comparing the rational parts together and the irrational parts together to form two different equations. The way I will picture surds would be like keeping a person in a jailhouse, where every Surdic number is a key. We will explore this illustration through the laws in the Surdic function. The first is the square root of a multiplied by the square root of a would give us a. This can be imagined as having two sets of the key, which is enough to open up the two locks. This will free the number inside the cell. For the second law, it states that the square root of a times the square root of b equals to the square root of ab. You can imagine this as having two different people inside the jailhouse, and you will need two pairs of keys to free them. Since we only have one key each, which is not enough to free them, the number remains in the jail. And since both A and B are in the same prison, they can be placed together, therefore square root of AB. This is similar to the quotient law, except you can imagine them as being on different floors of the prison house. For the next part, we see that we have two sets of square root of A and one square root of B. This means that the number A can be freed, while the number B will still remain trapped inside the prison house. The last law is addition and subtraction law. Unlike multiplication or division, you can simply factor out square root of A. One way to help you visualize it is by imagining that there are two different countries. The first one having n number of prison cells, while the second one having n number of prison cells. Let's try to see an example. We are asked to simplify the square root of 8 divided by the square root of 2. We can imagine that the two numbers are in the same prison cell, and so they can be combined together. And since it is a division, they are on the different floors. So, we can combine it and express it as square root of 8 divided by 2, which will become square root of 4, or simply 2. Conjugates are like twins with a bit of difference, and this idea is very commonly used in mathematics. For instance, in quadratic formula, we see conjugate roots being used when we place the plus or minus sign. Likewise, in surds, we also have conjugate surds, and the product of this pair would yield a rational root. This can also help us make a complicated looking fraction look more simplified. Let's take the example for instance. We can rationalize the root by multiplying both the numerator and denominator with the conjugate surd of the denominator. Notice how the expression is just simply multiplying by 1. Then, we can expand and simplify both the numerator and the denominator. This will give us 12 minus 3 square root of 2 whole thing divided by 9, which can be further simplified into 4 minus square root of 2 divided by 3, and this is our simplified form. When given an equation with the square notation, the solutions can be found by simply taking the square root on both sides. Doing so will result in having two answers, a positive root and a negative solution. However, if the question has given you the square root, we usually just use the principal root, which is a equals to square root of b. Let us take a look at an example. We are given the volume of the prism to be 14 plus 11 square root of 2. To approach this, we will need to first find the area of the trapezium base, which is simply the sum of the area of the rectangular and the triangular portion. From the given information, we will have the area of the rectangle as the product of square root of 2 and 2 square root of 2 plus 2, while the area of the triangle is half of the product of 2 minus square root of 2 and 2 square root of 2 plus 2. By expanding and simplifying the expression, we will have 4 plus 3 square root of 2. Next, we can go about finding the height of the prism. This will be taking the volume of the prism and dividing it by the base area. We then rationalize the denominator and simplify the expression to get 5 minus square root of 2. Today's lesson is quite long, so let us summarize what we have covered so far. We started with index numbers, which are simply number raised to a power, and illustrated it by having a martial artist drinking some energy drink. We also went through several rules that govern the indices before exploring the Surdic numbers. These are just roots which cannot be expressed as a fraction, or simply put, irrational. Just like indices, Surds also follow a set of laws. We then move to understand what Surdic equations are and learn to solve them through identities. As seen in quadratic formula, surds have conjugate pairs, which we can use them when rationalizing Surdic denominators. Lastly, there are also two solutions when taking square root